everybody, welcome back. This is Unit 10, Lesson 2, and in tonight's video we're going to be talking about the potential energy diagram. And really, potential energy diagrams show changes in energy that occur during the progress of a reaction. So what you'll find on the y-axis is always energy over here. What you'll find on the x-axis is reaction progress. So what that means is before the reaction begins, like over here, in the middle of a reaction, once it's occurring, which is here, you can see that these have collided, so this is during the reaction. RXN is our abbreviation for reaction. I'll write it once, and then I'm never writing the word reaction again because RXN is easier. And then when the reaction's over, so this is at the end of the reaction is over. So think of it kind of like beginning, middle, end. Okay? Actually, sometimes you'll see on this axis they also have time. So it'd be time also, but sometimes it's called reaction coordinate, and really what it represents is the beginning of the reaction before it really even begins, the middle of the reaction once the reaction's happening, and the end of the reaction, okay? And you'll notice it looks like a hill, okay? And there's really two shapes of these potential energy diagrams. I call them the fun sledding hill and the not so fun sledding hill. So if you were starting here, because this is always where you start, imagine sledding on this hill. You'd have to walk all the way up here, and then you'd only be able to sled down this little bit. This is the not so fun sledding hill. And I'll explain what that sledding hill represents in chemistry terms in a minute. But imagine this one. You start here, you only have to walk up this far, and then you get this big whee coming out. Okay, that's the fun sledding hill. Now, the part you have to walk up is the energy you have to put in, and the part over here that you sled down, that's the energy coming out. And so in this example, you would have to put all this energy in, and you'd only get this little bit of energy coming out. So in the not so fun sledding hill, more energy goes in than goes out, and as we know from previous chapters, that's an endothermic reaction, where more energy goes in than comes out. On the fun sledding hill, this is your energy going in, and this is your energy coming out. So more energy comes out, that's the fun sledding hill. More energy is exiting, that's exothermic. Okay? So there's really two shapes, and based on the shape of the curve, whether it's fun or not fun, you can decide if it's endo or exo. Like this one I just drew is a fun sledding hill, so it's exothermic. But this one would be a not so fun sledding hill, that's endothermic. So two shapes of the curve. And again, I explain that in more detail here if you need words. All right. There are 6 things that you have to be able to label on your potential energy diagrams. And I have descriptions of those things on the next page of your notes. Okay? 3 of these, if you notice, the first 3 are all potential energies. So the first thing is the potential energy of the reactants. Before a reaction begins, all you have are reactants. So the first line we're going to draw is a line to represent how much energy your reactants have. And if you look at the description, this line goes from the bottom of the graph to the top of the reactant line. This right here is your reactant line. So I'm going to draw an arrow to represent the potential energy of the reactants. It goes from the bottom of the curve to the reactant line. This is the potential energy of your reactants. This is number 1 on your description. Okay? It's the amount of stored energy that the reactants have. The second thing we have to label is the potential energy of the products. At the end of the reaction, all you have are products. This is your product line. potential energy of your products. Again, it goes from the bottom of the graph to the top of the product line. So this is the PE of your products. Okay? Now, if the reaction is endothermic, the potential energy of the reactants is less than. Like your reactant line is shorter than your product line. But if it's exothermic, the PE of the reactants is greater than the PE of the products. Okay? There's only one other potential energy we need to label, and that's the potential energy of the activated complex. This line starts at the bottom of the graph and goes to the top of the hill. Because before the reaction you have reactants, after the reaction you have products, in the middle of the reaction here, when you're at the top of the hill, we call this an activated complex. It's not reactants, it's not products, it's something in between. So this line, whoops, that starts at the bottom and goes to the top of the hill, that is the potential energy of your, I'm just going to put AC for activated complex. Okay? So notice, 1, 2, 3 potential energies all start at the x-axis and go to the curve. If it's to the first flat line, that's potential energy of the reactants. If it's to the top of the hill, potential energy of your activated complex. If it's to the second flat line, potential energy of your products. Okay? The potential energy of the activated complex is always the longest line on your curve. Let's see. Okay. I'm going to go back to a one-page display here. Okay. In addition to labeling 3 potential energies, we have to label 2 what we call activation energies. And activation energy, it's defined in number 4. Let me see if I can find that for you. We'll talk about it and then we'll label it, I think. Oh, not there. We're getting there. Okay. So number 4 here, activation energy of the forward reaction. Just like in class today when I burned the paper, things may collide, but they might not have enough energy to react. So this is the additional energy that you need to give the reactants to make them react. So it's the additional energy you have to put in. This does not start at the reactant line. It does not start at the x-axis. It starts at the reactant line. So it's the additional energy you have to give the reactants to get them to the top of the hill. So if we go here and we draw an arrow to represent that, which I think is here, okay, our reactants have this much energy. They don't start reacting until they get to the top of the hill. So the additional energy I have to put in is this much, okay? That's my activation energy, what we call the forward reaction. Activation energy forward. So in this case, it would be about, what, 250 whatevers, okay? Because they already have 200, and they need 450. So in this case, it would be about 250 whatevers, okay? Sometimes you could go backwards in reactions. You can turn products back into reactants. And again, the products require a little bit of energy to get turned back into reactants. So the energy you have to give the products to make it go backwards, that's activation energy reverse. And in this case, what is that, about 350 minus 450? In this case, that's only about 100, okay? So there's 2 activation energies. They start at the flat lines, and they go to the top of the hill. If it's the forward, it starts at the reactant line and goes to the top of the hill. If it's reverse, it starts at the product line and goes to the top of the hill. So activation energies do not touch the axis. The only thing that touches the x-axis are your potential energies, right? And then finally, the last thing that we have to label on this curve is something called delta H, or heat of reaction. Okay, so the last thing we have to label is this thing called delta H. And delta H is number 6 in your notes here. It has a bunch of different names. It has aliases. It's the heat of formation. It's also known as the heat of reaction, or it's known as enthalpy. And basically, no matter what you call it, it is always the energy difference between the products and the reactants. It's the difference in potential energy between the products and the reactants. And it's always products minus reactants. Okay? So this arrow floats between the product line and the reactant line. It doesn't touch the top of the hill. It doesn't touch the x-axis. Okay? If the reaction is endothermic, then delta H is positive because more energy goes in than comes out. Okay? If the reaction is exothermic, then delta H is negative. Okay? And again, we had already said for an endothermic reaction, the potential energy of the products is greater than the potential energy of the reactants. And that's really what these values are. I put H for energy, but you could also use heat, right? You could also write it as delta H is the PE of the products minus the PE of the reactants. Okay? And if it's exothermic, delta H is negative. So the PE of the reactants is greater than the PE of the products. So the second number would be bigger, which gives you a negative delta H. The beauty of this is you don't even have to memorize it. A bunch of different delta H values are given on table I. And if you look at the very bottom of table I, it tells you that a minus sign for delta H means it's exothermic. So it is right there on the reference tables. Okay, so if they give you a reaction and they want to know if it's endo or exo, you're going to use table I. This tells us if a reaction is endo or exo. Okay, because it gives us the delta H values. Okay, so let's just label delta H on our curve and then we're done for today. We'll go back to the curve. Where are you? There you are. Okay? We have 5 things. 1, 2, 3, 4. 1, 2, 3, 1, 2, 3, 4, 5 things. All we have to label is our delta H. And again, delta H floats between the product line and the reactant line. So I'm going to imagine that the reactant line was over here, and I'm going to draw a line down there, and that would represent the difference in energy between your products and your reactants. Okay? That's it for tonight, everybody. We'll see you tomorrow, and we'll practice this a little bit more and finish going over your test. Have a great night. Bye-bye.